Hi everybody, and welcome to the Cumulative Review Packet number 7 videos. I'm going to be taking you through numbers 1 to 9, which all refer to the beginning of Unit 5. So, if I take a look at number 1, we want to find the remaining trig functions given that cosecant is 5/3 and tangent is -3/4. And yes, we have done this before when we've used triangles. However, I want to use the new trig identity definitions because I want you to get better at them. So as soon as I see cosecant is 5/3, that means that I know automatically that sine, the reciprocal function, would have to be equal to 3/5. So I'm going to put 3/5 over here. So that one is done pretty quickly. As well as if I know that tangent is -3/4, I automatically know that the reciprocal function of cotangent is equal to the reciprocal -4/3. So those two pieces are taken care of pretty quickly. However, if I would like to find cosine, I need to use a particular definition. And from the trig identities videos, we know from Unit 3 that tangent of theta was equal to y over x. So it would make sense, because y is sine, that tangent of theta is equal to sine of theta divided by x, or cosine of theta. So since I know that this identity is true, tangent of theta equals sine of theta over cosine of theta, I also know that this must be true. If I cross multiply, I would know that sine of theta is equal to tangent of theta times cosine of theta. And if I want to get cosine theta alone, so I can figure out what it is, I can divide both sides by tangent. And I know that cosine of theta is going to equal sine of theta divided by tangent of theta. And so it's good for you to practice manipulating something you know is true. Here what we did was we really cross multiplied and did this times this equals 1 times sine. We then got cosine alone, and the reason that helps is now I know that cosine of theta is equal to sine, which is 3/5, divided by tangent, which we know is -3/4. And that is the same as 3/5 times the reciprocal of -4/3. The 3's on top and bottom cancel out, and so you're left with -4/5. So that means that my answer for cosine is -4/5, which means the answer for secant would be the reciprocal of -5/4. Numbers 2 to 9 are all trig identities, which in my opinion are puzzles to get what you have in front of you to be something more simple, or to eventually, as we continue through the unit, equal something that we tell you that we want it to equal. So, I'm going to make this a little bigger, and the goal of this is to simplify it as much as possible. And so I'm also going to pull up your packet as well, because this first problem, this looks intense. Cosine of pi over 2 minus x and sine of pi over 2 minus x. Now you might recall from the first video or your front of your purple packet that these are actually identities. So let me pull that up. If I bring this down, these are called the cofunction identities. So sine of pi over 2 minus theta is really equal to cosine of theta. So I'm going to come back to this, and I'm going to replace this with cosine of theta. And the numerator, cosine of pi over 2 minus x, is really equal to sine of theta. So let me pull that back up. So now, if my goal is to simplify this as much as possible, whenever I see sine over cosine, or y over x, I hope you're getting into the gut instinct of thinking about tangent. So the most simplified version of number 2 would be just tangent of theta. Number 3, methods that we talked about in the Unit 5 video so far, we could do a GCF if applicable, we could find a common denominator, we could just try to factor. However, whenever you don't know what to do, the last resort is to change something to just sines and cosines, because you're more familiar with that. So if I see tangent, I know that tangent of theta is equal to sine over cosine. So what if we replace this with sine of x over cosine of x? And then I see cosecant, and I say, you know what, I prefer it in terms of sine. So what if we replace cosecant with its reciprocal identity, 1 over sine of x, and then we have plus secant of x. We could change this to 1 over cosine, but let's see where this goes. If I am multiplying fractions, and I have the same thing on top and bottom, we're allowed to cross cancel. So this is really 1 over cosine of x plus secant of x. Now 1 over cosine is really the same as secant. So if I want to try to simplify this, let's get rid of the fraction and let's replace this with its reciprocal identity of secant of x plus another secant of x. And because they are like terms, the final answer is that there are 2 secant of x's. And so again, we're trying to get it down to one term if possible. In the first 2 examples, we were able to. Some of you might be wondering, why didn't I change this to 1 over cosine? I could have. I would have had 1 over cosine plus another 1 over cosine, but changing them both to secant gets rid of the fraction. Number 4, as soon as I see something that's squared, it makes me think of these Pythagorean identities over here. That's what always catches my eye. So I noticed that this one is more simplified than this one because this one has a subtraction problem. So I wonder if we can replace this with something from the Pythagorean identities. So I'm going to rewrite the numerator, cosecant squared of x, over. Now this piece, though, my eye goes to this identity right here. However, at this moment, this does not match this identity exactly. But what if I wrote the identity that I know is true over here? 1 plus cotangent squared of x equals cosecant squared of x, or theta, or whatever you want to call it. If I would like to get cosecant minus 1 on the same side, all I have to do is subtract 1 from both sides of the equation. And I would have that cotangent squared of x is equal to cosecant squared of x minus 1. So we can do some substitution. I know that this here is really equal to cotangent squared of x. So up here, I could write this as cotangent squared of x instead. Now that doesn't seem as simplified as I can get, because everything at this point could maybe still be changed to sines and cosines. So what if I said that cosecant is really the same as 1 over sine squared of x, and cotangent, we are dividing by cotangent, and cotangent is really cosine over sine, and if it's squared, it's equal to cosine squared over sine squared. So at this stage, just to save some room, I'm going to erase this. Feel free to go back if you need to see that again. But this problem now is a division of fractions. So it's 1 over sine squared of x divided by this fraction, which is the same as multiplying by the reciprocal, sine squared x over cosine squared x. Just like the last example, the sine squareds are going to cross cancel, and I am left with 1 over cosine squared of x. And 1 over cosine is really the same as secant. So 1 over cosine squared is really the same as secant squared of my angle. And that is the most simplified version I can get. Number 5, we're multiplying all of these, but I would say that it doesn't look like there's a greatest common factor we can take out. There's no fractions, there's no common denominator, there's nothing squared, so it's not a Pythagorean identity. So what if we just started replacing things with the popular reciprocal identities? For instance, I know that cosecant is really 1 over sine of x. I know that cotangent is really cosine of x over sine of x. I know that secant is really 1 over cosine of x, and sine is an identity or a trig function we're more used to, so let's leave it. The beautiful part about this is the canceling that we get to do, because when we multiply fractions, you can cross cancel. So this cosine and this cosine cross out. This sine on the denominator and this sine on the numerator cross out, because again, I'm just multiplying straight across in a way. So what I'm left with is just 1 on the top and sine of x in the denominator. So again, we have a fraction. Can we make this more simple? Well, I know that 1 over sine is really the same as cosecant because they're the reciprocal functions. So my final answer is cosecant of x. Number 6. So the goal of this one, I notice that I have a squared function. As soon as I have squared, I'm thinking maybe the Pythagorean identities will help us. But this does not match a Pythagorean identity yet. And so when I have two things being added, I'm thinking maybe a common denominator, but maybe a greatest common factor. Is there something in common between this first term and the second? Yes, there is. two cosines are in common. So if I took out a GCF of cosine squared of x, I would be left with sine squared of x, and then this would be gone, plus, if I take 2 cosines out of 4, I'm left with 2. So in the parentheses, I'm left with sine squared of x plus cosine squared of x. And I hope that this sounds familiar to you, because that is the most popular Pythagorean identity. Sine squared plus cosine squared equals 1. So that means that this sine squared plus this cosine squared must also equal 1. So this problem, what you're doing is you're taking 1 and you're multiplying that by cosine squared of x. 1 times anything is what we started with. So my final answer is cosine squared of x. Number 7 is a similar idea. Secant squared minus 1. Let's take a look at, let me erase this here. Let's look at the Pythagorean identities again because I see some squared terms. My eye goes to this identity here because I see something minus 1. So what if I moved the 1 to the other side? If I subtracted 1 over here, I would have that tangent squared of theta is equal to secant squared theta minus 1. And that is exactly what's here. So this can be replaced with what it's equal to of tangent squared. So tangent squared of y times cotangent squared y. So this was replaced with this because of the Pythagorean identity. What I now know is that cotangent is really 1 over tangent squared of y. And when I multiply by tangent squared of y, I can cross cancel. And there's really a 1 on the bottom, so I'm left with 1 divided by 1, which is just the number 1. Handy dandy, I have to say. Number 8, when I have a whole quantity squared, remember that really means the parenthesis times itself. So if I have a parenthesis times itself, I can do the distributive property, or as some popularly know it, FOIL. So we have sine squared x minus sine of x cosine of x minus another sine of x cosine of x. And yes, you could have written it as cosine sine. It is the same thing. And then negative cosine times negative cosine is a positive cosine squared of x. It looks like we made the problem more complicated. However, here's what I'd like to point out to you. These are like terms, so that would be negative 2 sine x cosine x. And also, if I wrote these next to each other, it's a similar theme to number 6. So if I look at sine squared plus cosine squared, I know that sine squared x plus cosine squared x is 1. So this can be replaced completely with 1, and so my final answer is 1 minus 2 sine x cosine x. The reason I like this problem is there's a hidden Pythagorean identity, and it's great to practice. Lastly, number 9 in this video, when you look at this problem, it's tempting to want to cross out the cosines. But as soon as there are plus or minuses in the way, that would be considered illegal. So instead, I see something squared. I look to see if I could use the Pythagorean identities, but I can't. So instead, what if we thought about factoring? What if we factored this numerator? Okay. So what times what gives me cosine squared? Cosine times cosine. What times what gives me 1? 1 times 1. How can I get the middle term of 2? Well, if I have 2 plus signs here and here, that would be cosine squared plus cosine plus another cosine plus 1, which would be 2 in the middle. Then I have cosine x plus 1 in the denominator. When the parentheses match exactly, when I have the same thing in the numerator and denominator, then you're allowed legally to cross that out. So my final answer for number 9 is cosine of x plus 1. And so in this case, because the Pythagoreans didn't seem like they fit, I said, why don't I rely on my algebra knowledge? And I know if something factors, what we really did, just as a quick aside, is this is the same as factoring x squared plus 2x plus 1. I really did x plus 1 times another x plus 1. But I had, instead of x's, I had cosines. And when they're the same on top and bottom, cross them out, and that would be your final answer. Okay. So guys, that's going to conclude this video for numbers 1 to 9, which is the Unit 5 material. You'll hear me next with the Unit 3 material. Thank you.